When infrared radiation interacts with matter, it causes covalent bonds inside molecules to vibrate. These vibrations obey simple laws of physics, like Hooke's law of vibration, which determines what the frequency is of a spring. We're going to see modes of vibration that are bends and stretches. Only modes of vibration that change the dipole moment of the molecule are available to be seen by the infrared spectrophotometer. The frequency with which covalent bonds vibrate depends largely on two factors: the mass of the atoms in that bond and the length of the bond itself. This is a harp. And if you pluck a short string, its tone is much higher frequency than a longer string. And the longest string has a lower vibration. This is a metronome. It can be used to demonstrate two functions about vibrating bonds. The metronome progresses at a tempo that is determined by how far away the weight is from the pivot. Longer bonds vibrate at lower frequency. Also, adding weight to the metronome slows it down. Bonds to heavier atoms vibrate at lower frequencies. This is an infrared spectrophotometer. Samples are placed in the path of a beam of infrared radiation that passes through the sample. This is a more modern infrared spectrophotometer. In this instrument, a liquid or solution sample is placed on this tiny crystal, and infrared energy is bounced off the underside of the droplet. This infrared instrument operates using Windows software, and when you first switch it on, it will do a system check, and then it will ask to run a background. A background scan is what we can use to subtract from our actual experiment data later all of the contaminants that are in the atmosphere directly above the sample holder. So this will remove water vapor, moisture, and carbon dioxide from our spectra. Scans run, and now this instrument is ready to accept a sample. Samples are administered in liquid or solution form by putting just enough of a droplet onto this sample crystal and then collecting a measurement. Go to measure, collect measurement. You have the option to give this a name. Our sample today is Nujol, which is a type of paraffin. And it will accept that information and the software gives you the impression that it is working by this green flashing light, but it actually isn't working until you press Start Measurement. The instrument collects scans of the same spectrum and then stacks them in computer memory. By doing so, noise averages to 0 and our signals reinforce. This gives spectra a much clearer overall picture at the end. Here is our spectrum. Currently, it's being shown as an absorbance spectrum, in that most light passes through, but these frequencies are absorbed. We're going to change that from absorbance to transmittance. And then this is our spectrum. If we go over to the left and click Pick Peaks, the software will identify the frequency of each of the peaks in the spectrum as wave numbers. This frequency scale is reciprocal centimeters, centimeters to the -1. When you're finished collecting your sample, very gently wash the optical crystal with a couple of drops of ethanol. The infrared spectrum gives us information about the frequency of stretches and bends within a molecule. The characteristic frequencies of vibration can be translated using a correlation table. Sometimes correlation tables are written schematically. Sometimes they're just a list. Ultimately, it's your task to interpret the spectra, and we can do that by reading the wave number of important signals and then looking in the correlation table to see what is a good fit. And I can tell that toluene, this molecule, has a carbon-hydrogen stretch here and a separate carbon-hydrogen stretch right there, because there are two different kinds of carbon-hydrogen stretch in toluene. There's an alkyl CH and an aromatic CH. And then just progress through the spectrum. Anything that happens kind of in this region is usually unreliable because many spectra have multiple lines here. And so trying to find something in amongst all of that mess is difficult. But here I have one that stands out on its own, so I'm going to go ahead and see if I can find what that represents. And it's in the region right here for a carbon-to-carbon double bond stretch. And then I have two very strong lines right here. And these represent bends. We find bends at these low wave number values. And these are carbon-hydrogen out of plane deformations. These are bends away from the plane of the planar aromatic ring. It's the 21st century, and we don't have to just rely on correlation tables from textbooks anymore. We can use software to help us find an answer. And here is toluene. This software is called iSpartan. It is the iPad version or iPhone version of Spartan molecular modeling software. And if you draw the structure, it will let you convert that into a three-dimensional model of the molecule, which it recognizes as toluene, and then we can predict the infrared spectrum. And as we progress through the simulated spectrum, it shows us the different modes of vibration. This is clearly a stretch. This is a carbon-hydrogen stretch on an aromatic ring. This is the carbon-hydrogen stretch on the alkyl substituent, this alkyl substituent being a methyl. Numbers given in correlation tables and in software do not necessarily represent exactly what you will see in your spectrum, because your spectrum is real life, and the software and the correlation tables are collected data or simulations of data. What's going on here is actually a carbon-carbon stretch of this double bond right here. This one and that one. In fact, all of the carbon double bonds in the ring are stretching. And if we go to low wave number, we can see the out of plane deformation right here. This is a bend rather than a stretch. And you can see that the hydrogen's waggling up and down. Okay, so with all of that collected data, what you're going to be asked to do is fill out a table at the back of the worksheet that says, this is the wave number, this is its shape, weak, medium, strong. You can also perhaps see broad. And then we're going to assign it. A nu is a stretch, a delta is a bend. So this is a stretch from a carbon to a hydrogen that is attached to the ring, and a stretch from a carbon to hydrogen that is part of an alkyl substituent. And go through and make assignments of all the individual functional groups that you can, and then draw a structure of the molecule. Submit your finished product to the Blackboard submission link.